Welcome everyone. My name is Kelsey Shaw. This is my first time doing the intro for the WESTalks if you are a return attendee. And if it's your first time, just a little bit about what we do. So this is an IC Impacts and UBC Future Water collaboration called Water and Environment Student Talks. So we aim to bring together leaders on sustainable water and environmental research from around the globe and engage students in these topics. And I'm gonna go forward, there we go. So IC Impacts is a pan-Canadian research center for international collaboration, and UBC Future Waters is a UBC group which focuses on disciplinary research at the intersection of law, policy, and governance. And so our WESTalks organizing committee consists of all of these wonderful folks who you have probably seen their faces before. So a lot of the committee is attending UBC, but we do have myself at the University of Victoria as well as a member at the University of Guelph. So even within our organizing committee, we're kind of all over the place. So one of the major sort of goals of WESTalks is to create space and dialogue from many different perspectives, geographically as well. And so something we like to do is, if this is your first time attending, it would be great if you could, we have this Padlet set up where you can put in your location of where you actually are in the world. And then it's always nice to see kind of who is where and what they're researching and studying. And I think the link will be in the chat. Yes. Perfect. So yeah, you can click on that in the chat and fill that out if you haven't already. And so today, December 2nd, we are going to have Dr. Monica Emelko talk to us from the University of Waterloo on treatment resilience in a changing climate. If you've attended our talks in the past, our most recent one was Dr. Ian Adler, and then this is a lineup of our future talks to come. So we have one more this year before the holidays start. And then we have quite an exciting lineup already, pretty much fully booked for next year as well. So stay tuned. And if you haven't had a chance to catch the previous talks, they are on YouTube, available on the IC Impacts channel. So without further ado, I will introduce today's distinguished speaker. So Monica is a professor of environmental engineering at the University of Waterloo, and she's a Canadian research chair in water science, technology, and policy. She holds a Bachelor of Science degree in chemical and environmental engineering from MIT, and a master's in civil engineering from UCLA, as well as a PhD in civil engineering from the University of Waterloo, which is also where I got my bachelor. So a little shout out to Waterloo. Her research is focused on drinking water supply and treatment and risk analysis for public health protection. She has advised the U.S. National Academics of Sciences, Engineering, and Medicine, US EPA, Health Canada, and several Canadian provinces and international governments regarding drinking water treatment requirements and health risk assessment, as well as source water protection and climate change adaptation. For the past 17 years, she has co-led the Southern Rockies Watershed Project team that is evaluating the effects of forested watershed land disturbances on hydrology, water quality, ecology, and treatability. This team was the first globally to describe wildfire effects on drinking water treatability, and among the first cited by the Intergovernmental Panel on Climate Change for identifying quality-associated threats from climate change to water security. Monica now leads For Water, a Canada-wide and internationally partnered research network of academics, water utilities, government agencies, industrial forestry companies, and NGOs focused on forest management-based approaches for drinking water source protection. So I think today's talk is very timely considering the recent events that have been happening in BC. and also just globally as we continue in this crazy world of ours. So without further ado, I will pass it over to Monica. And if you have any questions, please feel free to put them in the chat box, and then we'll have time at the end to address those.
All right. Thank you so very much for the invitation, first of all, to all the WESTalks team. I was just saying earlier, it's such an impressive group. I am really excited to speak here because you are the future. Students, postdocs, you're the ones who are going to be dealing with some of these challenges that we're faced with now. And while there's challenges, there's hope for science and for technology. So I'm very pleased to have the opportunity to share a talk with you that I'm the nominal author on, because I've pulled it together, but really this is based on the work of several individuals, collaborative work. And so I will certainly call them out and name them throughout the talk. So my name's up there just because I pulled the slides together. But these are people I've had the great opportunity to work with. Am I correct in believing that you can see my projected screen? Fantastic. So
sorry, we're not seeing it. Now it's projected.
Oh, super. Okay, so there's a bit of a delay. Thank you. So today's talk is about techno-ecological approaches for treatment, resilience, and drinking water security in a changing climate. And where this starts out is in my background and really the fantastic opportunities I've had as my career has transformed over the years. I was a treatment engineer, process optimization, a degree in environmental engineering, degree in chemical engineering, and I was really interested in making sure that public health was protected through the provision of safe drinking water. And of course, things aren't as easy as you treat what comes out of the pipe. And increasingly, we're learning that, but it's amazing that as recently as 1980, which is not that long ago, and please don't suggest to me that it is because I remember it. I was a young child, but nonetheless, it was the year of water, and we were still learning that if you dump problematic chemicals into the ground, that could be a problem. So we've really come a long way in 50 plus years since the 70s and 80s and Silent Spring. And so the thesis of my talk today is that I hope to inspire you to walk away with the thoughts about green technology. And this starts with some work that master's, soon to be PhD student Emma Blackburn has been involved in. It's this notion of what is green technology? We keep hearing about nature-based solutions. And so one of the things we've recently done with this topic is how does green tech apply to the water sector? The drinking water sector is very conservative. And one of the points that we've come out with is that, first of all, in drinking water treatment, technologies have to treat water to a certain level so that public health is protected. That is, they have to be fit for purpose in that regard. And what we found in thinking about this issue is, look, we need to be honest with ourselves. Whether technologies are green is not absolute. They're more or less green relative to one another, and it's a spectrum, not a yes, no kind of absolute. And so we can think about greenness from a variety of different perspectives. One of the most common is nature-based technology, so utilization of natural resources. And we hear a lot about nature-based solutions. Mother Nature knows how to purify our water. And we can talk about more or less nature-based in drinking water treatment. One of the big areas is, can we take advantage of biological technologies? We've taken advantage of them in wastewater treatment, municipal wastewater treatment, for example, but what about drinking water treatment? So this is a big area of discussion, but that's not the only aspect of greenness. A process engineer will tell you that energy consumption contributes to being green, or waste production, reducing waste production contributes to being green. Also, literal footprint can contribute to being green. So these are all different ways that we can think about green technology. And then as we start to engage in the discussion about nature-based solutions, I would like to propose, like many others have, that nature-based solutions, this concept is an oversimplification. And so really what we need to do is take, don't throw the baby out with the bathwater, take the good from technology and the built environment and the good from nature-based solutions and combine them to develop techno-ecological solutions for the very complicated challenges that we are facing, because we don't have time to sit and be idle. We need to do more. We need to adapt to the changing environment around us. And without safe drinking water, we can talk about a range of water values, but without safe drinking water, many of those other values of recreation, spirituality, ecosystem diversity will take a back seat. And so as we talk about techno-ecological nature-based solutions, we need to consider what we're trading off. And oftentimes when we go to a process that requires less human intervention, oftentimes, as you can see here with a range of drinking water related technologies, ranging from control of high rate clarification processes where we can respond very rapidly to large water quality swings, down to riverbank filtration, natural subsurface filtration, just combined with disinfection and really letting Mother Nature do most of the work in the subsurface. What we often give up is control. What if things change? How resilient will our treatment process be? And so I'm not here to say that everything should be gray built infrastructure, not at all. But I also don't want to kid myself. If we're talking about is your drinking water safe? And can your infant or can your family member who is immunocompromised because of a health condition, can they drink tap water? The notion of pure nature-based solutions is not feasible. There is a technological component, if only in the sensors that we use to make sure water is safe. And so the question is, where is that overlap? And there's a variety of ways that we can look at this. And so that's really the basis of the talk. And I'd like to present a few examples in that regard. So do we have less operational control with green technology? I have up here on the slide sometimes. And in fact, I would even go so far as to say often. And the challenge for us and for you in the future is, when do we need that control and where can we get the based solutions are not solutions if they don't have operational control. So let's talk about techno-ecological approaches. Now, where am I coming from? I said I'm a drinking water treatment engineer, and my bottom line is that water supply and treatment is not only important, it's in fact critical. It's really important that we all recognize that the major causes of death globally as we implement basic hygiene and sanitation, and it's not like we haven't been talking about that for the last 2 years with the pandemic. It's reminded us of that. Infectious diseases have dropped 3,000% plus as major causes of death in the last 100 years or so. And a big part of that, hygiene and sanitation. 4, in fact, of the major causes of death have changed because of basic hygiene and sanitation. In Canada and the United States, as you can see here, looking at infectious disease crude death rates, again, across a 100-year period, the first continuous municipal use of chlorine and our recognition of the importance of hygiene has advanced public health protection. We can't protect public health without treatment of some sort. And the paramount objective of drinking water treatment is protection of public health from waterborne disease, predominantly pathogens. And so one of the things we do when we regulate is we say we can't measure everything. We can't, it's too expensive to look for pathogens all the time. Any day it could change. So what we rely on is well-operated treatment. This is an image of conventional treatment: coagulation, flocculation, sedimentation, filtration, all of that to remove solids so we can disinfect and protect public health from waterborne pathogens. So how do we regulate? How do we assess public health protection, whether it's Canada, the United States, or elsewhere? We have many treated water quality criteria, so maximum acceptable levels. And then we also have a treatment technique-based approach, which is literally saying we will give you credit for treatment for things like waterborne pathogens like cryptosporidium, because we can't disinfect it easily. We also need to rely on its removal. We need well-operated treatment, conventional treatment, and we get credits for that. That's really interesting because, of course, the question is, all right, if we're saying that most surface water supplies require conventional or equivalent treatment, so filtration or something else, and this has been a big issue of discussion in British Columbia, we need to have that treatment, and we have to have it regardless of water quality because there's a risk there and we can't measure the pathogens all the time. And while filtration avoidance is possible, like in Victoria, British Columbia, for example, it's not common because it's difficult to prove that on a daily basis, your risk isn't changing, that pathogens aren't making their way into the water supply. So this is a great way of doing it. It's cost effective, but what it doesn't speak to is changing water quality and us as an industry, all of us being on top of it when water quality changes. How do we know? What are the signals we have? They're actually very limited. And in fact, what we see is as we start to look at cryptosporidium removal by filtration, in fact, it is not always more than this 3 log that is promised us for well-operated treatment. What does that mean? Right now we have turbidity criteria for does a filter work well? But in many cases, we've seen that that's not enough. And so what are the metrics we go to and how do we know our processes work well, especially as changing climate is changing source water quality? And we get to these ecological concepts of resilience. How do we measure resilience? How do we cross-apply these concepts from ecology where we have performance at one level, but if water quality changes because of a landscape disturbance like a fire or a flood, how do we know we're going to have that same treated water quality? Source water quality changes, will our system bounce back? Is it resistant to change or is it resilient? Or does it matter? Because we want both in treatment, because we want to protect public health. So these are the questions that we have to ask ourselves, and we really need to know, how do we ensure well-operated treatment? And this is an area our group is working in. So the point is, yes, technology can protect us, but we have to know how to use it, and we have to know its limitations, especially as source water quality is changing because of changing climate. And so we have to stop assuming that what's good for the fish is good for the people. Yes, ecosystem health and human health overlap, but they don't fully overlap. Drinking water security is an aspect of water security, but we all know there are trade-offs. What's good for one species of fish may be detrimental to another species of fish. So why would we think that what's good for fish in general is good for humans? And so what we need to recognize is that drinking water security necessarily involves making sure not only that we have high quality source water, but that we can also treat it. And we've had a lot of discussion around this. What does it mean to be able to treat water? Well, it depends on the technology you have and how well you can drive it. And so we have criteria that you can look up in textbooks. And it's amazing how a lot of those criteria converge onto only a few aspects of water quality. There's not a whole list of pathogens and contaminants here. If we can remove turbidity and color and carbon, we're actually well ahead of the game in terms of being able to treat water in general, because there are synergies in water treatment, and water treatment has evolved so that we can remove and purify water, not only in beautiful mountain water that you make beer commercials from in British Columbia, but also agriculturally impacted water, stormwater. Heck, we can make safe drinking water on the space station, right? We can reuse water. Question is, how much are people willing to pay for it? And how much are we willing to pay to distribute it across long distances like this vast continent on which Canada sits, right? So these are the questions and the challenges, and we can't keep just, oh, I'll just punch a new hole in the ground and make a new supply. Those days are gone. And if we're going to talk about drinking water security, we need to talk about treatability. And if we're going to talk about treatability in a changing climate, we need to talk about resilience. Landscape disturbances in a warmer world are around us. I remember when I first started doing research on wildfire over 15 years ago, and we were regularly told, we were perfectly consistent in not obtaining research funding. We were regularly told, wildfire is a Western issue, it's a one-off. And of course, wildfire, you can't read the news now without hearing about wildfire. And wildfire is not a disturbance that is in a vacuum. Flood and wildfire go hand in hand. And of course, flood exists on its own. In the East, excuse me, in the East, hurricanes happen and we have blowdown of forests. And when we reduce our natural treatment capacity, which is so integral to Canada, the forested landscape, natural purification. Easily over 2/3 of our population is impacted by the forests with respect to water supply. When those are disturbed, our water supply is disturbed. The question is to what extent and how quickly can we recover? Excuse me. So what do we do in moving forward, knowing that these disturbances are coming, and also recognizing another important part of the discussion that I'm sure many of you have been involved in, which is the recognition, the very important recognition that climate change undermines assumptions of stationarity. And as you can see on this fantastic paper from the USGS, Millie and others, Bob Hirsch is on there, climate change undermines a basic assumption that historically has facilitated management of water supplies, demands, and risks. It's this concept of stationarity. And what that means is that things like water quality vary within a range. And so in that upper left diagram, you see natural variability in water quality. And part of the reason why water quality varies naturally is because of weather, hydroclimatic variability. You have wet years, you have dry years, right? Varies within a range. The blue line in that upper left corner is stationary, but it's an upward trend. It's a trend stationary process. What non-stationarity means is a variety of things. It could mean a shift. We're at one level, all of a sudden we're at another level. That's what the upper right plot shows. And when most people think of water quality after landscape disturbance, that's what they think of. But that's not usually what they get. It's not like I have 1 NTU of water regularly in my source on average, and it goes up to 100 on average. That's not what we get. If that was the case, it would actually be kind of easy to treat, because we can treat any water quality, especially if it's constant or consistent, right? What makes our lives hard is when it's variable, because then we're trying to get things right. And if you need operational control to get things right because things are fluctuating, you need resilience. And so here's the challenge. If things are fluctuating, do we have technologies that can be responsive? And response often means a human input, because we don't have the sensors to say, well, what kind of carbon change is it? How much more coagulant do I need? AI isn't there yet, and we don't have the sensors to be the inputs to artificial intelligence. What happens usually with changing climate and disturbance is the bottom two, where you have on the left of the bottom of these plots, plot C, you have increased variability, change in variance. Or the nightmare scenario, which is a unit root process, where things are changing, they're kind of getting worse, but it's unpredictable. Sometimes things drop down. We really don't know what the functional relationship may or may not be. That's challenging. That's where climate change is pushing us. It's not the top row, it's the bottom row. And the question is, what are we going to do about it? So one of the stories, and I will get back to green technology, but let's make sure we're on the same level of information with respect to what climate change does first. So we started working, like I was saying, about, I said 15 years ago, and I'm a little bit in denial because it was actually in 2003. So it was a little bit more than 15 years ago. But we started working on wildfire, and we said, you know what, we're not going to be fire chasers. This is just this project we happen to be involved in. And the problem is, and this was in Alberta, the problem is fires kept happening around us. Not only in Alberta, but in British Columbia and in Ontario and all over the world, even in areas that are not historically fire prone. And so we found ourselves in this situation going, oh my gosh, I guess I'm learning about sources and fire and hydroclimatic variability. And the thing is, on these landscapes, regardless of where you are, yes, all the landscapes are different, but one of the commonalities is if your fire is big enough and severe enough, water quality deterioration can be expected. The question is, what kind of deterioration and how long will it last? But what we saw in many of these sites, like you can see here, is the two photos on the left were what we started off with. The two middle photos, you know, we had these periods of intense deterioration in water quality. And so you can see that in the middle photos. But then that went away and you didn't see the effects visually as much. But there were shifts in the ecosystem. And we started seeing secondary effects. And so the longevity of these impacts is not something that has been extremely well documented, but they're real. Now, are our landscapes resilient? Absolutely. Have they been subject to severe fire before? Absolutely. If you look at the Rocky Mountain, there's a historical project called the Rocky Mountain Project, and you can see that all of southern Alberta at one point was, all the trees weren't there because they'd been burned. It's about 120 years ago, which incidentally is about the typical lifespan of those forests on average, because they burn, and that's part of the natural ecology of the system. And so, yeah, our landscapes can bounce back. But the thing is, we're pushing climate change, we're pushing these disturbances to an unnatural rate. And so while we can engage in the discussion of natural resilience and recovery of the landscape, the problem is that we're now having disturbances on disturbances. And so that natural resilience of the landscape is likely not there in the same way. And the other part of it is these recovery periods are on the 100-year timescales. That's beyond our typical lifespan. And so that's insufficient wait time. And so again, from a techno-ecological perspective, the question is, what can we do to support these ecological or nature-based processes? And one of the things we see when we think about some of the disturbances you might see on these landscapes is, if you look in these plots, we've got sediment and carbon, the two drivers of treatability, plus phosphorus, because that's implicated as the primary vector for primary productivity in these water supplies. It can certainly contribute. It won't guarantee primary productivity and proliferation of algae, but it certainly contributes to it. And it's certainly more likely if you see phosphorus. And what you see if you look at natural disturbances, so we've got reference, which is undisturbed, or more appropriately, not recently disturbed. Then we have things like floods and fires, and this is just a snapshot. I'm not proposing that these numbers are absolute. But then we have forest harvesting of different types, old school harvesting, contemporary harvesting or logging. And what we start to see is Mother Nature punches well above her weight class with respect to some of these disturbances. They can be transformative on the landscape and potentially catastrophic for the provision of safe drinking water. And certainly high quality systems have the most to lose. But also what we've seen is that systems that are already challenged, the wildfire of 2016 in Fort McMurray on the large Athabasca River, 100,000 square kilometer watershed, 6% of it burned. That's about 6,000 square kilometers. The river already looks like chocolate milk, and the landscape is not steep like in other parts of the mountains. This is the boreal. Here you've got a flat landscape and an incised river. And so you think maybe a lot of those impacts won't make their way through the groundwater or through overland flow into this big river system. But you know what? They did. And even though this river looks like it's already severely deteriorated, and fire was on top of the water treatment plant, but thankfully it was upstream of the urban environment, so we didn't have those challenges to deal with. What we saw is these plumes coming out of the watersheds. So this is another study we did in conjunction with Alberta Environment and Parks. And these plumes, when you get into a big river, when you go back to remembering your hydrology, you go, my goodness, what happens in big rivers when you have a plume? Are they well mixed? No. It's kind of more like a tiger stripe pattern. You have poor lateral mixing in these systems. And so these plumes directly fed into the water treatment plant in Fort McMurray. Thankfully, some brilliant design in Fort McMurray that they have not one, but two reservoirs in series. So they can manage some of that in their reservoir. But the trade-off is we get rid of some of those solids. We start to transform some of the carbon. It's a beautiful place for algal blooms to happen, though. Those sediment-associated nutrients like phosphorus just build up in the reservoir. They build up across the watershed. So you've got this big bad river, and it's still bringing these materials in preferentially. Depositing in a reservoir, and we're getting algal blooms now, not only in the reservoir, but in the water treatment plant, trading off one problem for another. We need the holistic resilience in the treatment process. And so hopefully if we can manage some of these nutrients, we can manage the blooms. Can we manage the challenges associated with those blooms? Absolutely, but boy, did the cost of treatment go up. And more recently, what we found is it's not just treatment, but also the increasing risks of algal blooms. So absolutely, as we look at coagulant dosing here in Fort McMurray, were we able to treat water, and have we been able to check it out at pilot scale and really demonstrate it that it can be done even if it's the blackest water? Not surprisingly, yes, this was Jesse Skorik's PhD work. He's now a postdoc working collaboratively with our team in the city of Calgary. And we did some piloting work there, and absolutely these technologies work, but they cost a lot of money. And they still don't guarantee us that these problems will be treated. So for the algal blooms, currently Fort McMurray for a community of 60,000 is about $9 million in. And when all is said and done, if we end up building an ozonation plant there, I bet it'll be at least 50 million plus. So that's the gray infrastructure that's going in. And so the question is, what more can we do on the green side to balance off some of these trade-offs? And of course, people, if you think globally and you look globally, a lot of the discussion is around supply diversification. So let's not rely on one supply. Here on the right, we have San Diego. Their issues are, of course, drought. They're looking for different water sources, including now seawater desalination and recycled water, which is advanced treatment of wastewater, right? Because they've depleted their groundwater sources, they've depleted the surface water sources locally, so they're really looking to diversify. That's great if you have access to all those sources. Another big approach that people are using is supply diversification, which means trading, right? So if one system is above its targets for conserving water and another system is below, they can trade credits for some form of payment. It may not be cash, but it's some form of payment. Maybe they exchange services. Those approaches work, but they don't really get at the underlying problem. And if you're landlocked with limited number of water supplies, especially like many rural, remote, and marginalized communities where this is not as easy to do, what do you do? And so a big area where we've been focusing is source water protection. And so let's talk about what that means and the balance between techno-ecological approaches for source water protection. Historically, we've got the Keating Channel. This is here in Ontario. It's the outlet through which the Don River empties into Lake Ontario. A big part of historical source water protection was all about managing discharges. And of course, here we see that stormwater is tough to manage. And there are various approaches to improving management of stormwater, and they include a lot of nature-based or nature-inspired solutions. And here globally, we see that a lot of these approaches, they've worked. Managing and maybe even minimizing discharges to our water supplies works. This is an example here of source water quality, and this is nitrate levels. This is from the UN. So nitrate concentrations at river mouths, and this speaks to agriculture. And so we see in many parts of the world, we have decreased levels of certain key contaminants. But here's the thing. This is great, but we need to do more. It's not just about discharges, because when we think about discharges and the notion of here's my beautiful watershed, I'm going to protect it and conserve and put a fence around it and have a protected area, the important part to remember is that Mother Nature does not see that fence. Mother Nature doesn't care about the fence, especially when Mother Nature is all worked up because of climate change. These extremes in weather that we're seeing on a regular basis. And so source water protection is evolving. I've got a few more slides and I'm hoping we can engage in this discussion. So we've talked about technologies in plants and techno-ecological approaches like filtration. And then we've moved on to talking about techno-ecological approaches, now moving all the way across to hybrid approaches that may be on the landscape, maybe reservoir management, for example. Now let's go all the way to the source. So let's talk about source water protection at the source. Forests are critical in Canada, they're critical globally, yet they're the one compartment of the environment for which there are no best management practices with an eye to water, especially safe drinking water. And that is something that the For Water Network is trying to change. Source water protection is evolving because we need to get in there and actively protect our forests. And the way we're talking about doing it in this contemporary sense is not to put a fence around it and say no discharges, but rather to help increase resilience and really resistance and resilience in forests, if you want to be clear about the ecology of the system. But more broadly, generally speaking, increase resilience. And we can increase resilience by increasing diversity in the forest and helping reduce fuel loads, helping make sure our forests are healthy. Healthy forests equal high quality or healthy water. And so this is the wave of the future in source water protection on these natural wildland landscapes. And so this is a techno-ecological nature-based solution. It's helping Mother Nature be as strong and resilient as possible. And so a big part of that, what we're working on, and this is now Suzanne Baramian's master's work, and she's now a PhD student as well, we're looking at best management practices for managing risks in forests from forested watersheds. And what we're seeing, which is not perhaps the most stunning, is that if we force ourselves and invest in best management practices, which are more expensive, we can help forests be more resilient. And regardless, I won't get into all of the different cut approaches that we applied at, this is field scale, and when you're looking at forest management, you know, not large for a forest, but certainly large scale for a drinking water treatment engineer. What we saw, if we looked at carbon, for example, is we can manage forests, the releases of carbon by implementing best management practices on the landscape. So I won't get into the different cutting approaches here, but let's just say that there's several contemporary forest management approaches. The last two are a little bit higher with the partial cut. But it's really hard to find reference watersheds. And so it's really important to note that in that system, the DOC levels were naturally higher. That's what you see with the light blue. So it would have been nice to have them all line up, but we're literally identifying replicate watersheds, if you can imagine. So it's challenging. So I just want to note that. So even at the source water protection scale, are forests critical infrastructure? Absolutely. But I would argue that yes, conservation is a great step forward, but we can't have it all. We can't have all the fish species we want because some like more turbid environments and some don't. So we have to make choices, and those choices involve trade-offs. But I would propose to you that source water protection needs to move to the domain of techno-ecological approaches that involve utilization of the landscape, but also protection of the landscape to ensure not that nobody accesses it, but rather that it is resilient. And if that means we have to access and work with the landscape to be resilient, so be it. So techno-ecological approaches can take on a variety of configurations. And the key part of it, of course, is focusing on what we want to achieve and recognizing what the trade-offs are in achieving those goals. So I hope that this is some food for thought. I really think these are issues we're going to be addressing in the future, and I hope we can have nice, clear, and honest discussions about what these approaches can do and what they can't do, so that we can develop meaningful solutions for the very complex and wicked challenges that we face and need to address in the future. I have to say that this work is not possible without partners. We have the privilege of working with a variety of partners, and they're listed here. You can't do good science without good partnership. So I'm very appreciative. Of course, I'm appreciative of my lab group and all of the students I have the privilege of working with. I've highlighted some of their work here. Thank you so much for the opportunity to be here. I'd be so happy to have a discussion if anybody's so inclined. Thanks again.